Welcome to today's paper reading. Today's paper is titled, Efficient Bias Mitigation Without Privileged Information. This paper was published on AR14 by Mateo, Espinosa, Zarlenga and colleagues from the University of Cambridge and Sony AI. The abstract highlights a significant issue in deep neural networks where performance disparities are observed across different groups, particularly when group and task labels are spuriously correlated. For instance, the correlation between grassy background and cows can lead to biased performance. Existing methods to mitigate this bias often rely on group labels for training or validation and require extensive hyperparameter tuning, which can be impractical due to data size and computational constraints. To address these challenges, the authors propose a new method called Targeted Augmentations for Bias Mitigation, TAB. This framework is designed to be hyperparameter-free and leverages the entire training history of a helper model to identify spurious samples, thereby generating a group-balanced training set. The proposed TAB method is shown to improve worst group performance without needing group information or model selection, outperforming existing methods while maintaining overall accuracy. The success of deep neural networks, DNNs, is often overshadowed by their tendency to exploit biases within their training sets. In visual datasets, which are crucial for many consumer-facing AI models, these biases are known to be exploited and amplified. The difficulty in addressing these biases stems from their ubiquity and diversity, which can arise from spurious correlations, underrepresentation of various elements, and other factors. This raises significant ethical and legal concerns, particularly when DNNs are deployed in critical tasks without awareness of these biases. As a result, there is a growing need for effective bias mitigation strategies in vision models. Figure 1 illustrates the process of targeted augmentations for bias mitigation (TAB). The process begins with training a model f theta on a given training set D, while keeping a record of each sample's loss at every epoch. This historical loss data is then used to split samples of each class L into two groups, a minority group D-L and a majority group D+L. This is achieved by clustering samples based on their entire training histories. To construct a group-balanced dataset, each minority group D-L is upsampled to match the size of the majority group D+L. Finally, f theta is trained from scratch using this augmented dataset, aiming to improve the model's robustness by addressing biases through targeted augmentations. In this paper, the authors study bias in supervised learning, specifically focusing on spurious correlations within the training data. They define a training set trained consisting of pairs of samples xi and labels yi, drawn from a distribution train x, y. The goal is to learn the parameters theta of a deep neural network, DNN, at theta that accurately maps each sample to its label. Traditionally, theta is learned by minimizing the expected value of a loss function, which is approximated using empirical risk minimization, ERM, and gradient descent. However, when spurious correlations exist, ERM can exploit these shortcuts, leading to unfair treatment of bias-conflicting samples. This issue is often hidden by population-level evaluation metrics. Therefore, the authors introduced the concept of worst group accuracy, WGA, to analyze model performance across all population subgroups, ensuring a more comprehensive evaluation. In the context of bias mitigation in deep neural networks, DNNs, research has primarily focused on two main approaches: bias mitigation, BM, and bias discovery, BD. BM methods can be either group supervised, where subgroup labels are available, or group unsupervised, where they are not. Group-supervised BM techniques include distributionally robust optimization, DRO, and reweighting or rebalancing samples. Group-unsupervised BM methods aim to discover pseudogroup labels or use loss functions that incentivize group robustness. On the other hand, BD methods analyze biases in datasets through error-aware models or human-in-the-loop visualizations. Our approach stands out by adopting a practitioner-first strategy, eliminating the need for hyperparameters, complex pipelines, and group annotations, making it more practical for real-world applications. Figure 2 illustrates the accuracy dynamics throughout training on the Waterbirds dataset, focusing on different subsets of validation and training samples. Specifically, it shows the accuracy for a. bias-conflicting validation samples, B. Bias-aligned validation samples, C. All validation samples, and D. Bias-conflicting training samples. The shaded area highlights a period where the loss converges, indicated by plot D. During this convergence, the validation worst group accuracy, WGA, increases, as seen in the green segment of plot A. Simultaneously, the bias-aligned accuracy, plot B, and mean accuracy, plot C, experience temporary decreases, marked by red segments. This suggests that during training, models may initially prioritize learning simpler, bias-aligned features before gradually improving on harder, bias-conflicting samples, leading to fluctuations in overall accuracy metrics. The paper explores the challenges of bias mitigation without privileged information, such as group labels during training or validation. One major challenge is overfitting to validation biases, where the validation set mirrors the training set's distribution, leading models to exploit spurious correlations. Another issue is misleading early stopping, where deep neural networks tend to learn simpler hypotheses first, which can result in temporary decreases in average accuracy. These factors make mean accuracy-based model selection prone to rejecting models that generalize better. The paper introduces the price of unawareness, PO, a metric that measures the cost of lacking group labels for model selection. PO is the ratio between the best theoretically attainable test WGA and the actual test WGA when hyperparameters are selected based on mean validation accuracy. A PO greater than 1 indicates that the absence of validation group annotations leads to a model with worse WGA than what could have been achieved with proper group-annotated validation sets. Figure 3 illustrates the test WGA, worst group accuracy, for various hyperparameter configurations of ARM, Mastune, LFF, and JTT on the Waterbirds dataset. The crossed yellow bar indicates the model with the highest validation accuracy across each method. Notably, this model exhibits 1. A lower WGA compared to the model selected using validation WGA, starred bar, and 2. A similar or worse WGA than an equivalent ERM model, dashed line. This suggests that the selected models are as biased as their ERM counterparts, indicating no effective debiasing occurred. For clarity, the ranking of each model based on their validation accuracies is displayed above each bar. Figure 4 illustrates the training dynamics on two datasets, Waterbirds and Celeb, focusing on the identification and dynamics of bias-conflicting samples. In panel A, the fraction of bias-conflicting samples identified during training is shown, indicating how effectively the model distinguishes between bias-conflicting and bias-aligned samples. Panel B presents the loss dynamics for bias-conflicting samples, dashed lines, and bias-aligned samples, solid lines, highlighting the differences in learning curves between these two groups. Finally, panel C shows the proportion of bias-conflicting samples and the subsets discovered after clustering the training samples based on their entire loss histories. The smaller cluster, labeled in red, consistently has a higher proportion of bias-conflicting samples compared to the overall training distribution, as indicated by the green line. This demonstrates the effectiveness of clustering based on loss histories in identifying bias-conflicting samples, which is crucial for targeted augmentations and bias mitigation strategies. The proposed targeted augmentations for bias mitigation, TAB, pipeline begins by constructing loss history embeddings. This involves tracking the training loss of all samples throughout the training process. These embeddings encode the loss for each sample at each step. Next, the pipeline performs loss-aware partitioning to separate bias-conflicting samples from bias-aligned ones. This is achieved using k-means clustering with k equals 2, partitioning the data on a per-class basis. Finally, the pipeline generates a group-balanced training set by upsampling underrepresented subgroups, thereby enhancing the group representation in the dataset. The experimental results demonstrate that TAB significantly improves worst group accuracy, WGA, across various tasks, showing a consistent high WGA not observed in competing methods. Additionally, TAB achieves competitive mean accuracy against ERM models, maintaining high accuracy even when biases are absent. In terms of computational efficiency, TAB's pipeline leads to shorter training times and less model selection time compared to other methods, making it practical for modern workloads. Table 1 presents the means and standard deviations of worst group accuracy, WGA, price of unawareness, PO, mean model selection WGA, MMS, and average accuracy for various bias mitigation methods. The models are selected based on validation accuracy over each method's hyperparameters. Notably, TAB, which is hyperparameter-free, consistently achieves better WGA than ERM across all tasks. The PO metric indicates that competing methods incur a significant cost due to their hyperparameter searches, often leading to biased model selections. Conversely, TAB maintains a high WGA without the need for additional hyperparameter tuning, suggesting its effectiveness as a bias mitigation alternative. Figure 5 presents a dual analysis of mean accuracy and computational efficiency. On the left, it displays the mean accuracy of TAB and ERM models as the correlation strength varies in even, odd, and CNIS datasets. This variation helps in understanding how these models perform under different levels of bias. On the right, the figure illustrates the worst run wall clock time for all methods tested in the CNIS dataset, represented by solid bars, and the total model selection time relative to TAB's worst run, depicted by crossed bars. This side of the figure highlights the computational efficiency of each method, providing insights into the time-performance trade-offs involved in model selection. Table 2 presents the representation of bias-conflicting, BC, examples in the original training set train and in TAB's augmented training set train. The top section shows the percentage of BC samples in both sets across different tasks. The bottom section details the fraction of training BC examples correctly identified as underrepresented in TAB's loss history clustering. This analysis highlights how TAB's augmentation leads to a more group-balanced dataset, with significant increases in BC sample representation, particularly in tasks like even, odd, and celeb A. The results underscore TAB's effectiveness in identifying and upsampling underrepresented BC samples, contributing to improved group balance and potentially informing future data collection strategies. The TB method, while effective in improving worst group accuracy without group labels or model selection, does come with certain limitations. Firstly, the model training loop needs to be run twice, which can be a constraint when dealing with massive datasets. Additionally, TAB requires storing the loss history matrix, which can significantly increase the size of the training set and thus training times. Despite these computational costs, the method operates without the need for costly model selection. Another limitation is the requirement for k-means, a method that faces scalability issues with large datasets. However, the use of mini-batch k-means has shown to be a scalable solution. Future research could focus on improving TAB's performance in highly imbalanced tasks by exploring symmetry and variant transformations, learning better discriminative embeddings, or exploiting additional information. Thank you for watching.